Electrochemistry is the study of the interchange of chemical and electrical energy. We have two types of cells, voltaic/galvanic. In a voltaic cell, we have a spontaneous reaction, or thermodynamically favored, which means our delta G is negative. This would be like a battery. It's going to run on its own. We also have electrolytic cells, which need energy because they're non-spontaneous or not thermodynamically favored. In these cases, our delta G is positive. You can think of this as whenever you plug in your battery, you're having to put energy into it, and then the voltaic is when it goes on its own. We're going to be focusing on voltaic galvanic today, and then later we'll talk about electrolytic. Everything in this unit has to revolve around redox reactions or oxidation-reduction reactions. Remember that oxidation was the loss of electrons, LEO, and then reduction was the gain of electrons, GER. So LEO goes GER. Remember that when it loses electrons, it becomes more positive, and if it gains electrons, it becomes more negative. Here we have a redox reaction when permanganate reacts with iron 2 ion. We produce manganese with a +2 charge and iron with a +3 charge. So when these collide directly, no work is actually obtained because it's just going to be released as heat. In a voltaic or galvanic cell, though, we can convert that chemical energy to electrical energy. The oxidizing agent, which is the substance that's reduced, and the reducing agent, which is just simply the substance that's oxidized, are separated, requiring that in order for the reaction to occur, that electron is going to be transferred through a wire. The current produced in the wire can then be directed elsewhere to provide useful work. So that's going to look like this. In that previous example, we had our iron +2, and it was going to lose an electron to manganese or permanganate. So the electron is going to get transferred from iron to permanganate through a wire. But when I move that electron over, I'm not going to be able to keep moving electrons over because I'm going to have a buildup of negative charge, and the electron's not going to want to go to permanganate anymore because there's a buildup of negative over here. That's why we need a salt bridge. A salt bridge allows ions to flow between the two solutions to keep the net charge at 0. We can have a salt bridge like this, where we have a gelatinous mixture of some salt that's not going to react. Sometimes we also just have a porous disc that allows for ions to transfer both ways. Very important that the salt bridge contains an ionic substance that does not react with either half cell. So you want to choose ions in the salt that would normally be spectators. Think of your solubility rules, things that are always soluble, like potassium nitrate or any group 1A nitrate. So potassium nitrate, sodium nitrate. We could use even sodium acetate. Acetates are always soluble. But we want to choose things that are soluble. If I chose sodium chloride, there's exceptions to chlorides being always soluble. So if I had silver, lead, or mercury in either of these half reactions, then I would form a precipitate, which would cause my concentration to change, which we'll see later in the chapter. So again, make sure that you're choosing group 1A nitrates are generally our best bet, but as long as it doesn't react with either solution in the half cells. If you remove a salt bridge or don't put one in at all, then the voltage becomes 0. The flow of electrons are going to stop, since the charge imbalance between the half cells will prevent electrons from flowing through the wire. That's what we were talking about a second ago. Once one electron moves over, it's no longer going to be able to transfer another electron. In an electrochemical cell, the reaction occurs between the electrode, which is going to be our metal, and the solution. The reaction only occurs against the metal and the solution. Some vocab that you need to know is anode and cathode. Those are the two half cells. One is called the anode and one is called the cathode. Oxidation occurs at the anode. Reduction occurs at the cathode. So one way of remembering is we have unox and red cat. I can never remember who's red, the ox or the cat, so I remember it as the vowels go together and the consonants go together. So A and O and R and C. Unox, red cat. And then electrons always flow from anode to cathode. So fat cat. From anode to cathode. So pause the video and figure out which process occurs at the cathode. If you said reduction, you're correct. Remember those consonants go together. Red cat. Cell potential, or EMF, is the pull of electrons from the anode, the substance being oxidized, to the cathode, the substance being reduced. Remember, electrons are flowing from the anode to the cathode. We measure that in volts, and volts are joules/coulombs. In our very last section, we'll talk more about volts in the joules/coulombs when we have units canceling out, but for now, you can just know that they're measured in volts with a voltmeter. So we put a voltmeter on that wire so we can measure the amount of voltage going through the wire. In this problem, they gave you a reaction. When they give you the reaction, they've already told you which reaction is being oxidized and which reaction is being reduced. So the first question says, which metals should we choose? Well, we have a metal here and a metal here. So we should use copper and we should use silver. Then, which substance is being oxidized? Oxidized means it should become more positive. Well, copper becomes more positive. It goes from a 0 oxidation number to a +2 oxidation number. And then silver ion is being reduced. It gains electrons. It goes from a net +1 to a 0 oxidation number. Which substance is at the cathode? Well, the cathode is where reduction occurs. Reduction was silver ion, so silver is my cathode. And then my anode is where oxidation occurs, and copper was oxidized, so copper is my anode. Let's go ahead and skip this question for now about the salt bridge, and let's calculate the Ecell for this reaction. When they give you the reaction, we're going to use that reaction to determine which reaction is going to stay as written and which one is going to be reversed. We're going to look at this chart, which is the standard reduction potentials, which is in the back page of your notes. On the AP test and on many times on a problem, they'll give you these two half reactions that you need instead of giving you the entire chart. So first we need to find the copper reaction. Copper is going to a +2, so we want the one that has copper and +2 in it. So this one here. And we want the silver +1 and silver metal, so this one here. Looking at it, notice that we go from silver plus to silver metal. That's exactly as this one's written. So we're going to leave this one as 0.80. And then the other one, we should be going from copper metal to copper +2. So this one needs to get reversed. When we reverse it, just like when we've done Hess's law and other problems, we're going to do a -0.34. We're going to change the sign. So 0.80 plus negative 0.34 gives us 0.46 volts. That's the voltage of this reaction. Let's look at what this reaction looks like in a simulation. So the first thing we need to do is choose our metals. We want to choose copper and we want to choose silver as our metals. So we're going to click on metals and we're going to choose silver. And if we have silver metal, then we're going to want to bathe that in a silver nitrate solution. We want the metal and the solution to be the same metal. Copper, we're going to choose copper metal, which means we need a copper ion in solution, so copper nitrate. Notice we have a blue solution since it's copper nitrate. And we want 1 molarity for our concentration. You can change the molarity, but that's going to change the voltage. And we just calculated that the voltage should be 0.46. So when we turn it on, let's see if we get 0.46. And we do. Notice that the electrons are flowing from the copper to the silver. We said that copper was the anode, and so we're going from anode to cathode. Let's look a little bit closer at the reaction. And we can also see that copper solid is turning into copper ions. Sometimes on the AP test, they'll ask what happened to the mass of the anode, or what happened to the mass of copper. Well, we can see from the balanced equation that we went from copper to copper ion, so that should be decreasing in mass. But we can also see that in the simulation that since it's losing electrons, the copper is going from metal to ion. So the mass of the electrode is going into solution. On the other side, we have silver, and silver should be going the opposite way. We have silver ions turning into silver metal. So the silver ions are plating onto the electrode. So the silver electrode is gaining in mass and the copper electrode is losing mass. Before we go and answer that question we skipped, let's draw out what happened. You should be able to have a spot in your notes to draw this. So we have our 2 containers, and we have our electrodes. 1 electrode was silver and 1 is copper. And then we have our salt bridge. Don't forget your salt bridge. Inside our silver, we said that silver is the cathode, and we said that copper is the anode. In the cathode, we should also have some silver ions, and copper, we should have some copper ions. And it was copper plus 2 from the reaction. Remember, our reaction was... We also need to have a wire for our electrons to flow. So if we were to draw it, we would say that the electrons are going from the anode to the cathode. So those are our electrons. You should also say that the anode is where oxidation occurs. Oxidation means that I'm losing electrons. So I'm going from copper to copper ion. Again, I can also see that from the balanced equation. And then my silver is being reduced, so it's going from ion to metal. I can clearly see from this picture then that copper should be losing mass and silver should be gaining mass. Our cathode is referred to as the positive ion and the anode is the negative ion. Our electrons flow from anode to cathode. They're flowing towards the positive electrode, which makes sense. And finally, if I had KNO3, which was the question earlier, notice in the cathode I'm losing positive ions. So I need the positive ion of the salt bridge to migrate into this part of the half reaction. And then over on this side, I'm gaining positive ions, so I need the negative ion to migrate into this cell. So the question was, if our salt bridge was present, the K would be going to the, so K is going to be going to the cathode. Another way that you can remember it without writing it out each time is K, or potassium, is a cation because it's a positive ion. Cations go to the cathode. Nitrate is an anion. Anions, or negative ions, go towards the anode. Here we have the standard hydrogen electrode. The standard hydrogen electrode consists of a platinum electrode in contact with a 1 molar hydrogen ion solution bathed by hydrogen gas at 1 atm. Basically, I have hydrogen ions and hydrogen gas. The standard potential for this half reaction is 0. In other words, we base all other reduction potentials on hydrogen. So they react lithium with hydrogen, sodium with hydrogen, gold with hydrogen, so that way they can get those reduction potentials. One thing of note is it says that we have platinum as our electrode, because notice that in our reaction we don't have any metals. We have an ion and we have a gas. So looking back at our last example, had we not had, let's say, copper going to copper ion, maybe we had copper ion, so copper plus 1 going to copper plus 2. If that was the case, we would have both ions in solution, and this would have to be a platinum electrode. So then our copper and copper plus 2 can react on the platinum electrode, but the platinum electrode wouldn't gain or lose mass because it's only facilitating in the electron transfer. I just have copper going to copper plus 2. So when there's no metal involved, we use platinum, since platinum won't react with any of the substances. Standard conditions for all of our electrochem equations will be 25 degrees Celsius and 1 atm. We saw those also in our thermodynamics section. And 1 molarity. That's why when we were choosing our solutions, we had to choose a 1 molarity solution. So finally, to determine the EMF, or the E, of the cell, when they don't give me an equation, we use the standard reduction potentials. We're going to choose the one that's most positive. That's the one that's most easily reduced. Therefore, it's going to stay as written. The other reaction will be reversed, and the sign of the EMF will be reversed as well, which is what we saw earlier. Since the number of electrons lost must equal the amount gained, the half reactions must be multiplied by whole number integers to achieve a balanced equation. The value of E naught does not change when the reaction is multiplied, unlike when we do like a Hess's law where we would reverse the reaction and multiply. Our equation technically is Ecell is equal to the reduction plus the oxidation. So looking at how that would look in a problem, we have our 2 half reactions, and they gave us the Ecells. Remember that you could get these values from the standard reduction potential chart if they weren't given to you in a problem. But unlike the problem that we solved earlier, this one doesn't have a balanced equation, so we've got to determine who's going to stay as written and which one's going to be reversed. This one is more positive. Since it's more positive, it's going to stay as written. So our Ecell will be 0.77 plus, and then this one will be reversed, and our sign will flip, so negative 0.34. Adding those together, we get 0.43 volts. Now for my balanced equation, I have 1 electron and I have 2 electrons. So I only need to multiply the top reaction by 2. I don't need to multiply both of them. Sometimes I multiply one, sometimes I multiply both, sometimes I don't have to multiply either. So I've got iron with a +3 plus copper metal, because remember I reversed that reaction, goes to copper +2 plus 2 Fe2 plus. Remember that your electrons are going to cancel. That's why I didn't write the electrons. But I should have 2 and 2, which would cancel them out. I should not have electrons in my overall balanced equation. If you had a problem that said write the half reaction for the equation that occurs at the anode, anode is where oxidation occurs. Oxidation was the one that was reversed. So copper goes to copper 2 plus 2 electrons. And the reaction that occurred at the cathode is the one that stays as written. So those are my reactions that occur at the anode and cathode.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution, and the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a voltmeter to the cell shows that electrons flow from zinc to copper. The voltmeter reads 1.103 volts. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The overall cell reaction can be written like this.